In previous videos, we talked about some of the basics about creating what are called Lewis structures. So we should probably touch base with what that means. In video 1, we talked about single bonds and how to count valence electrons. And that's necessary to get us to multiple bonds and some of the other things. In video 2, we talked about multiple bonds. And we talked about how we need sometimes double or triple bonds. Now we're going to talk about probably the biggest topic yet. And this one has to do with a variety. First of all, we're going to talk about ions. We'll talk about expanded octet. And we're going to talk about resonance. And so this is going to be difficult in the sense that you definitely need the other videos before you start here. So let's go with the idea of expanded octet first. And there are times when we have structures that need more than 8 electrons on the outside. For example, if we have PCl5, then right away we're going to say, well, how do we draw this structure? Well, let's add these up, and you have 5 electrons here plus 5 times 7, so that's a total of 40 electrons that are going to go around this structure PCl5. Now what we do is we draw a skeletal structure, but this time we're not going to draw it with only 4 things around it. Because there's a 5, what we're going to do is draw it as this arrangement here, and maybe you could do this. So each of the chlorines goes on the outside. Now some of this is based on experience, okay, but you'll start to see them. In other words, we wouldn't do a situation where we would have this kind of arrangement. You know, that might seem like, well, yeah, but we have to because we have 4. But in this case, that's not what we do. Now, the reason behind that is a little complicated for us, but we can at least address the idea that when we have the periodic table here, a little bit of chemistry for you, is that these atoms here, actually also have a d orbital available. Okay? That's not true with the ones above them. If you remember, these end with 2s2 and 2p something. Okay? But here we have 3s2, 3p6, and then there's also this d that is available, and that's why we're allowed to do that. So generally the ones that we're going to see will include these and any of these. Okay? So be ready for it. These also. All right. So what do we do now? We have PCl5, and we simply have to draw the remaining electrons. If you remember, though, we have 5 times 2. So we have a total of 10, and we have to get up to 40. And so what we do is we just add the dots here. Now, I know I tell you to go furthest away. This is nice to have a marker rather than a skinny old pencil, but that's what PCl5 would look like. Okay? Seems kind of odd, but that's what we do. So this is called an expanded octet. What that means is it's beyond 8, obviously. Okay? So let's see if we can do another one, because it doesn't always end up with having 5 bonds around the outside. And a classic example would be something like XeF4. Or we could try XeF2 and see what that does. So the general idea here then is that we have 8 electrons for xenon, and 2 times 7 equals 14. So now we have a total of 22 electrons that need to go around this structure. So we draw xenon here and the 2 fluorines. We now have a total of 4 electrons, and we need to get up to 22. So let's just color those in. So we have 2, 4, and then 6, 8, 10, 12, 14, 16, 18, 20. Now what do? Well, this is why we have an expanded octet. If we look at this closely, we've only got 20 electrons, but we still have 2 more to go. And it turns out that they go on the central atom, because the central atom is actually big enough to do that. Okay? What we would probably draw, though, is a structure like this, axis with the F's, and then I'm going to cheat a little bit and draw those things like that. But probably the 6 rather, would go around like that. You should draw those as dots, but I want to save time on the video. So that's really what we, and still there's 5, 2, 4, 6, 8, 10. There's 10 electrons, but that is 1, 2, 3, 4, 5 things. We call them domains, by the way. It's kind of a upper chemistry thing, but yeah, those are called domains. Okay, so that's how you would do XEF2. SF6 would be a similar idea. So that is what we call expanded octets. Okay, let's look more closely now at something called for ions. Okay, because there are some special conditions that we have when we're talking about ions. And generally, the idea is that you use brackets. Okay, that's one thing. And then counting electrons is a little bit different when you're dealing with ions. Okay, so what are ions? Ions are charged particles. Pluses or minuses, basically, that's all you need to know. All right, so what do we do with charged particles? Let's start with a simple example of NH4+, ammonium ion, NH4 plus 1. And it's also written as NH4+. How do we do this? Well, when we count them again, we have, for example, 5 electrons for nitrogen. We have 4 times 1 for the hydrogen. But this guy here, because there's a plus 1, it actually means that we subtract. It means we are less an electron. Right? How did you get a positive charge? By losing an electron. So this structure really, instead of the 9 here, we actually only have 8 electrons. And I'll show you now. This one's a little uncommon because we have a plus charge, but that's what happens here. And so what do? We draw this nitrogen here, and the 4 hydrogens go around the outside. You remember that nitrogen only needs, hydrogen only needs 2 electrons each. So we've used up all 8 electrons. But here's the difference. When you do ions, you also have to include this, those brackets, and the plus 1 here. It tells us that there's something different. Okay, so the phrase I use is to keep your eye on the bracket. So when you have ions, right, keep your eye on the bracket, right? Look for the bracket. Okay? And the reason we do that is because sometimes we have 2 structures that if we didn't have the bracket, we would get them confused. And a classic example would be SO3, which is sulfur trioxide, a poisonous gas. But we also have SO3 2-, which is called the sulfite ion. And so these 2 are different. This one would get brackets and this one would not get brackets. Okay, let's try another example here. And we could go with carbonate. Carbonate is CO3 2-. Okay? We're going to save you time and not make you do the whole structure here. Okay? But it turns out that you would have C, and then O, and O. We would end up having this arrangement. Okay? And we'll talk about why do we have a double bond here and so on. But because it's an ion, you have to draw the brackets there. Okay, so that shows us that we would have the carbonate ion. Okay, so that's really all you need to know about ions, is that you have brackets, and then you have to include the oxidation state, is what that's called. But now we should look at something a little more complicated. Okay, This concept is called resonance, to resonate. And resonate means to go back and forth. Right? That's the idea of resonance. Something goes back and forth. When we have music, resonance means that it causes a vibration in something else. Okay? So, what do we have here with resonance? Let's take a simple example. And the idea of oxygen, when it has 3, is actually called ozone, right? And it's supposed to be a protective layer from the sun. Okay? So ozone here, what do? We have 3 times 6. It gives us 18 electrons around the outside of ozone. So you draw your skeletal structure here. And then you have to get up to 18, if you remember. So we have 2 and 4. We have our time saver here. 6, 8, 10, 12, 14, 16, 18. And there's a reason why I draw them to the outside, because now we'll see that the central atom is deficient, right? We can see that there are 8 electrons here, 8 electrons here, but in the central atom, right, there's only 6. Okay? So, what we're going to end up doing is sharing these 2 electrons with the central atom. But wait a minute. So let's say we do that. The other side would only have single. Now we can color them in. And that's what we would get, right? Everybody has 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Everybody has 8. The problem is that somebody on the other side of the classroom might have said, we decided to share these 2 electrons. Right? So option 1 could have been this, and option 2 could have been that. So now it's possible that somebody said, well, we decided to do this. And why is one better than the other? Well, one isn't better than the other. And you might say, well, wait a minute. If I flip this over, I get the same thing over here. Kind of true, but there's 1, 2, 3 electrons here, and we would call this 3, 2, 1. In other words, they are distinct. I mean, they are separate atoms. So we draw both of them. You don't have to put the numbers in the middle. And then we draw this double arrow to show that there's something called resonance. Okay, so when you draw ozone, you have to draw this structure and that structure. I'm going to give you a little bit of information here. There are no ozones with a double bond. And there's no ozones with a single bond either. And you'd say, wait a minute, how can that be true? You just drew them. You simply drew a double bond and a single bond, double bond, single bond. How is that true? Because the idea of resonance is that these 2 structures together actually make, that's how we draw that. But what's really going on is that, let's say there's a single bond here, okay? But remember, we have a double bond and a single bond. So what happens is it's averaged. So we could say it's 1.5. That's really what's going on. Okay, so we could draw like this. We could draw like this maybe, that there's 1.5 bonds. But when we test ozone, we never get a test that says, oh, there's a double bond and there's a single bond. It doesn't happen. So you have to draw both. That's how we do it, with the double arrows. But in reality, this has 1.5 bond strength for each of those. Let's take the toughest example that you're going to see. This is like carbonate, which we talked about before. The nitrate ion, NO3 has 5 electrons plus 3 times 6. And this time, because it's a negative, we get 1 more electron. That's how we do it with ions. Okay? That -1 means you have an extra electron. We had ammonium, we had a +1, so we count less. But now we have nitrate with a -1. So we have 5, 3. And the reason it's there is because it makes the whole thing stable. NO3 without that extra electron doesn't exist, falls apart. Doesn't matter to us. That's the general idea. Okay? Now, when we go to draw nitrate, there's your 6 electrons. We need to get up to a total of 18, 19, 24 electrons. We currently have 2, 4, 6. And then what happens? We have to get up to 24. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I always draw them away from the central atom. It just works best. Okay? To save you time, though, I'm not going to show you now everything that we could do, but instead I'm going to show you one part of our class might say, oh, to make nitrogen complete with 8 electrons, we put our double bond on this side. And the other group said, well, we prefer this. And then the third group said this, okay? Well, none of them is more correct than the other, and in reality, we have to draw all 3 versions of this, and that's why this is a tough one, okay? So now let's do that. Let's draw this nitrogen here, and we'll draw 3 versions. That way we have, you can see all along, 3 versions. Let's draw the first one with the double bonded oxygen here. We'll draw this one with the double bonded orange, and this one with green. Okay? Just to show, right, that's the general idea. Now for the rest of them, we can draw it as black, I guess, right? Right? So one group decided the double bond goes here, another here, and another here. And we still have to draw the rest of the unshared electrons. Okay? Remember though that because oxygen's electrons here, those, all these electrons, the double bonded and those want to be as far apart as possible. So that's the way we draw them. Okay? And so now that is one structure, and we keep going. It's a good idea to have a big fat marker to save you some trouble. And then this guy. So here's the other thing about resonance, though, is that none of these stands all by itself because they all exist. But don't forget, these are ions. So we have to draw, keep your eye on the bracket. You have to draw that. And then finally, we have to draw the -1 oxidation state, or the charge. And then finally, as if it didn't take long enough, we have to draw lines between them, right, to show that that's resonance. So on a quiz, when you get NO3, you have to draw all 3 of those. None of them exist all by itself. There are no double bonds in nitrate. There are no single bonds in nitrate. Now what we have is they take this single bond, let's say, and we divide it by the other bonds. So each bond is actually the nitrogen-oxygen bond. I'll draw a little thicker here, is actually 1 1/3 bonds. So when we test its energy, that's what we get, 1 1/3 bonds. So that's the general idea of resonance here. I think it'd be a good idea if maybe we tried one more. Let's see what happens if we try N2O. N2O. I don't really know if that's going to have resonance or not. I know that it's not an ion. I have 2 times 5 plus the 6. we have 16 electrons going around N2O. Because oxygen is the fewest in number, we draw oxygen in the middle. And then we need to get up to 16, so we have 2, 4. And we have 6, 8, 10, 12, 14, 16. Right? But what happens in this case? This will not be resonance, because if I share 2 electrons here, 2 electrons here, the final structure ends up just looking like this. There's double bonds, okay? We put them 120-degree angle. So in this case, we would not have a resonance structure because there's no variety here. So let's make sure we understand what's going on with all of these examples and get us through Lewis structures 3. All right. The idea is that in previous videos we talked about single and double bonds. And now we're talking about ions in these other 3 cases here. There are times when you have to put more than 4 domains like bonds or unshared pairs around a central atom. But you don't do this in some cases. And it's partly experience. But here's PCl5. And so when we add all of those up, it turns out that we're going to have 5 things around phosphorus. And there's a reason it can do that, and that's because phosphorus has a D group available. So phosphorus actually has this place where we could put more electrons. That's not true with that row 2. Okay? Now for xenon, when we draw it out, it doesn't look like we have more than 4 things, but when we have extra unshared electrons that we didn't get rid of, they go around the central atom. And if you look, this does include what we call 5 domains. There are 5 places or regions that are needed. 1, 2, 3, and then these. So we still have 5 domains. It's still considered what is called an expanded octet. Here now, one of the new things is that ions are positive and negative structures, and we have to include brackets. And the other thing is that counting electrons is a little bit different. We've talked about this. If you have a plus, you actually end up subtracting the total number of electrons, okay? But the trick is keep your eye on the brackets. So if you have an ion, look for brackets, okay? And so here's another example of a carbonate ion. You have to draw the brackets, and then this is called the oxidation state. Okay. Now, there are times when we draw some structures and we have some options. In other words, we have multiple possibilities. Okay. When we drew this ozone, for example, we could have drawn a double bond on the right, or we could have drawn it on the left. And it turns out that both arrangements are possible, but neither one of them really exists. In other words, resonance means that you have a combination of these two, and so you get something like this. So what we really draw is both structures, but it turns out that neither double bonds or single bonds exist. Here's the most complicated version, and I think it's a good idea to memorize or at least practice this, be able to do this, because once you know how to do this one, you're going to be pretty invincible as far as resonance structures. We did one final example here to make sure, and it did include multiple bonds, but it is not a resonance structure because we don't have any other options. So that wraps up Lewis video number 3.